Hello, I hope all of you are doing well out there. Let's give this a go and see if we can make some videos to finish off the lecturing part of 310. I'm going to come up with a way to do some forecasting, but we'll do more on that later. Okay, the chapter that we're currently working on is the evolution of a baroclinic system, and we went through the adiabatic processes during our last lecture before spring break. Now let's talk a little bit about the diabatic effects. So remember that a diabatic process involves a transfer of heat energy between the air parcel and the surrounding environment. So the release of latent heat is one example of a diabatic effect. For this section though, the heat transfer between the Earth's surface and the atmosphere will be the primary diabatic effect. The pattern in which the heating and cooling occurs is critical. The differential heating or cooling of air at a given location with respect to the surrounding region causes the development. So air over a warmer surface will be heated from below. Obviously, air over a colder surface will be cooled from below. So these processes will aid in the development of low and high pressure systems. Diabatic heating is the forcing mechanism for the thermal low associated with continental tropical air masses. So remember, there's thermal lows and then there's synoptic lows. So a thermal low is just a broad area of warm temperature on the surface, which will correlate to a region of low pressure. Diabatic cooling is the primary forcing mechanism for the cold polar high associated with the continental polar air masses and or Arctic air masses. So here again, there are things, thermal highs, and there's also synoptic highs. The thermal highs are shallow, and they're just there because of a broad area of very cold air near the surface. So in North Dakota, we've had numerous thermal high pressure systems move through this past winter when we've had strong polar and or Arctic air mass move through the vicinity. So the Baroclinic instability, this is the process linking thermal terms and divergent convergent terms, is baroclinic instability. So the situation that we see here on the right is we have a wave coming off the leeward side of the Rocky Mountains, and we do have warm air advection out ahead of it, and we do have some cold air advection that's sneaking in on the back side. So over time, due to the baroclinic instability, the wave did amplify over time. So note we have a much better looking short wave 12 hours later than we did 12 hours earlier. So long waves, as we talked about, are are relatively stable. They're more so on the barotropic side. But what we want to concentrate on are major short waves because they're more likely to amplify due to baroclinic instability. And remember too that the major short waves were associated with temperature advection in the lower levels. So differential heating leads to a strong north-south temperature gradient in the mid-latitudes. The temperature gradient, in combination with the Earth's rotation and the interaction of the atmosphere with oceans, land masses, and terrain features, causes the natural large-scale wave pattern or long wave pattern in the westerlies. The temperature gradient is the source of potential energy which baroclinic systems tap as their strength. In order for a major shortwave to amplify significantly, there must be a large energy transfer from the temperature gradient to the wave. The potential energy of the north-south temperature gradient is transferred to the major shortwave by thermal advection throughout the troposphere. So basically what it's saying here is naturally we're going to have a deficit of energy being received at the polar regions, and we're going to have an excess of energy being received at the equator. So the Earth must balance out that differential, and we're going to see that long waves and short waves are the driving mechanism to force the air to move together and neutralize the imbalance that is caused by the Earth-Sun relationship. So here's an example where we do have a strong temperature gradient at the 850 millibar level. So in southern Minnesota, some of the temperatures in the southwestern Minnesota are about 10 degrees Celsius, as you can see in the yellow. Southern Canada, up through this region, we see that the temperature is around -5. So we do have a very strong temperature gradient in that distance, what should we say, approximately 350 miles north-south direction. So over on the right hand side is the 850 millibar map showing you the ISO heights and also the ISO tax for that region. So the next one is taking 24 hours later, and notice how the trough really intensified over that 24-hour period, in part due to that strong temperature gradient across Minnesota up into southern Canada. So that strong temperature zone is what we call a baroclinic zone. So the thermal advection aloft, coupled with temperature advection around a well-developed surface system, causes the upper level wave to amplify. The greater the amplitude of a short wave, the greater the energy associated with the short wave. A well-developed baroclinic system on the surface must be present to ensure thermal advection throughout the troposphere. As the potential energy is transferred from the temperature gradient to the short wave uses the energy to develop the low-level circulation of the low or high pressure system. So the low-level circulation, or the wind, is kinetic energy, energy of motion. Energy is made available to the system when warm air rises and cold air sinks, which is associated with mid-latitude systems. And rising and sinking air is also going to be kinetic energy. So we have warm air moving northward ahead of a baroclinic low or behind a baroclinic high. Cold air moving southward ahead of a baroclinic high or behind a baroclinic low descends. So this is what I've shown you here is we have strong warm air advection out ahead of this particular system, and in the yellow, in that area over here in the yellow, that is ascending air. And then with the strong cold air advection back through parts of Wisconsin into North Dakota, Minnesota, then we kind of go neutral or to the blue side, which is descending air motion. So this particular chart is the 700 millibar vertical motion in centimeters per second. So the development of the systems as a cyclogenesis and or anti-cyclogenesis proceeds, the thermal advection increases and more energy is transferred to the wave. The energy then strengthens the low-level circulation. The process continues unabated until some mechanism causes it to stop. So I'm going to concentrate more on cyclogenesis than anti-cyclogenesis, but remember, all low-pressure systems will develop to a point and then they will stop. And so in a bit we'll get to the processes that will cause the development to stop. So baroclinic instability is the primary mechanism responsible for the development of mid-latitude synoptic scale systems. These systems help maintain the global heat balance by transporting warm air northward and cold air southward. Only 0.5% of the total potential energy of the atmosphere is available for conversion to kinetic energy. Only 10% of that 0.5% actually gets converted to kinetic energy. So imagine the consequences if we are able to convert more of the potential energy to kinetic energy. And this might be part of the argument on the global warming / climate change scenario, because heat is energy, and so that's going to create more energy to be possibly changed to kinetic energy. Hence, some people say that we are having more severe weather outbreaks, and it's pretty obvious that our hurricanes seem to be reaching Category 4 and Category 5 more often than they did decades ago. Okay, so next on the list, again, just a little bit of review. Remember, for large-scale conditions, cyclogenesis is favored by certain large-scale conditions. In the long-wave pattern, cyclogenesis typically occurs at and just downstream from the long-wave trough axis. So I've found a pretty decent looking long wave, and I put in the trough axis for you. And note where the surface low did develop out ahead in the area of difluence aloft. So in that region between the ridge axis out ahead of the system back towards the trough axis. Okay, things that, as you know, we've already covered in lecture. So intense cyclogenesis normally occurs in troughs with a negative tilt, and here is the negatively tilt trough. Remember, it goes the northwest through southeast. So we compare that to lines of longitude, which are given here, and so this system is just a little bit on the negative side as shown on this graphic. What do negative tilts do? They will enhance the amount of difluence out ahead of the system. Therefore, they could support stronger cyclogenesis. Now, if we do have positively tilted troughs, and here's a good example of a strong positively tilted system, and they're orientated northeast through southwest. More often, these type systems are associated with non-developing systems. So that's why when forecasting and analyzing troughs, amplitude, locations, and tilt, you want to find the troughs that are at best neutral or going negatively tilted. Those are the ones that will help aid in a more rapid cyclogenesis on the surface. So the jet stream pattern, the relationship between the jet stream and cyclogenesis is also very important. Cyclogenesis typically occurs under difluent flow aloft, which is associated with supergradient winds. Upper level troughs are likely to intensify when the wind speeds upstream of the trough axis are greater than the wind speeds downstream from the trough axis. So we've took a look at this slide earlier in the semester, so just a little review. If we have straight line flow, gradient wind, the contour gradient force is the same here as the Coriolis force, and so the vector was parallel to the isoheights. But as we move into a region where the isoheights spread apart, we are going to lose the speed of the wind because the contour gradient force is going to decrease, but it's going to take a while for the Coriolis force to adjust, and therefore the new vector is pointing down towards regions of higher heights. Now eventually the Coriolis force will be in balance again with the contour gradient force, and we'll go back to a geostrophic flow. But in this area in between, we can force the trough to amplify and dig towards the south, in this case towards the equator. And as that amplifies and digs, then the amount of difluence out ahead of it can become a little bit stronger. So this is an example where we have the stronger winds on the backside of this particular short wave that we have right through here. Surface low, not very well organized, but we do have some lee cyclogenesis that is starting to occur. And then, hard to see the numbers, but later, 12 hours later, we can see that the wave axis is a little more negatively tilted, which will enhance the amount of difluence out in this area. And here is the surface low. Now it's well defined as it kicks out into the central plains. So the shortwave troughs strengthen as they move into long wave trough position and become negatively tilted downstream from the long wave trough axis. Short wave troughs intensify under diffluent upper flow, which is common in negatively tilted troughs. So again, note the importance of a negatively tilted feature versus a positively tilted feature. So the negatively tilted diffluent major shortwave trough may stack 1 to 3 degrees to the southwest per standard level to a baroclinic low. And again, it's just showing you that baroclinic lows will have a tilt with height. Now they're just trying to give you an average degree of tilt when we're talking lines of longitude. This trough must be present to support the baroclinic low. The baroclinic low must be present to ensure temperature advection occurs throughout the troposphere. This will promote wave amplification. So baroclinic instability is the link between the upper and lower level features. Baroclinic instability converts the potential energy of the north-south temperature gradient to kinetic energy of the disturbance. The strongest north-south gradient occurs along the polar front. Consequently, baroclinic lows form along the polar front. So this example, just note we have a very strong negatively tilted system, ridge axis over here, and so you expect the surface low to develop in this vicinity. There it is, with a secondary low back here. So the secondary load's more stacked, so this one's probably more on the barotropic side, and then it looks like we have a baroclinic system developing off the mid-Atlantic states. And as that trough rotates up, you can see it here now, pretty intense, very strong vorticity field indicating that we do have strong diffluence in that vicinity, and the low is situated here, and it did intensify. Now I know it's kind of hard to see the numbers, but here at 00Z it was 997, and at 12 hours later it was 988. So it did drop 9 millibars in a 12-hour period. Okay, so that's where we'll stop for phase number 1. We'll come back and pick up on the Patterson's rule in video number 2. I'm going to try to limit the size of these videos somewhere between 15 and 20 minutes. So we'll stop here and pick up with the Patterson rule in video number 2.